Hi, Physics 2. Mr. Janowski here. This is the first part of the Chapter 33 slides. So on this slide, we have the do now question. It's all of the metric prefixes, and we're not going to go through these one by one right here. That would take too long. The key is just that we use these in science all the time. It's very handy and very helpful and saves a lot of time and effort if you just get good at these. And the pattern to see is that they go in powers of 1,000. So base, then kilo, then mega, et cetera, going up. And going down, you have the base unit of the thing. Then you have milli of that thing, then micro of that thing. And it's just important in science to get kind of fluent in these things. It makes life easier. So the next do now question, think back to last year. What are the units of energy? That would be the joule, named after this guy, James Prescott Joule. What is the first law of thermodynamics, aka the conservation of energy? Well, it's that, the conservation of anything is that that thing can't be created or destroyed. And mathematically, we were writing it this way. Sigma E sub I plus sigma W external equals sigma E sub F. So the sum of your initial energy, take all of the energies you have at the beginning, add them all together, plus factor in any sources of external work that you have, and that will tell you how much energy you need to have in total at the end in all of the different forms of energy. So that idea will come back several times in this chapter. And the fourth question, what are the two formulas we learned for gravitational potential energy, GPE? Well, in chapter 9, when we first did energy, we learned that GPE is mgh, and that works if you're always near the surface of the Earth. So Alice goes to the top of the slide and then goes down. How much GPE did she have at the top of the slide? Things like that. And then the other one in the gravity chapter, we learned this more complicated one. GPE equals minus G M1 M2 divided by D. And that is the more general formula that works when you are dealing with big distances. So things that are, falling from very far out in space towards the Earth, for example, that kind of thing. So now we begin chapter 33, electrical potential energy and electrical potential. I didn't name these things. If it were up to me, I would have named them differently because their names are going to be confusing to people who are learning them for the first time. Just be aware at this point that electrical potential energy is not the same thing as electrical potential. It's messy. So yeah, here's the GPE formula. And again, this works if you're starting and ending your problem near the surface of the Earth. So you raise a book over the floor and you drop it. Okay, you are always near the surface of the Earth, so you use this formula. If you're dealing with bigger distances, you have to use this one. So GP is equal to negative all of this stuff. So why is this negative? It's negative because GPE in this context is like a debt. It's energy that you kind of owe to the system. So what that means is if you're anywhere near the Earth and you want to end up infinitely far away from the Earth, you have to put energy into the system to beat the gravity between you and the Earth, basically is how it works out. So that's why it's negative. Think of it as a debt. It's energy that you owe the system if you want to get away from it. So look at this formula and try to see what happens to GPE if the masses are separated by an infinite distance, with infinite in scare quotes. Well, if you're dividing something finite, so big G times N1 times M2 is going to be some finite number. If you're dividing that number by infinity, you end up with 0. And this is not the mathematically rigorous way of writing it. It should be like limit as D approaches infinity of this, whatever. Save that for math class. In physics, it's quicker and easier to write it this way. We're dividing by infinity, even though technically you're not allowed to do that. I'm going on too much about this. The point is, if you divide something by infinity, you're going to get 0. If you divide something finite by infinity, you're going to get 0. All right, now I'm being pedantic. So anyhow, notice that our EPE formula for electric potential energy looks very similar in form to our GPE formula. Just replace the G with a K, the M's with Q's, and distance stays the same. And the minus sign, we'll deal with the minus sign in a second. But yeah, just like last chapter, Coulomb's law, F sub E is equal to K Q1 Q2 over D squared. Looks a lot like Newton's law of universal gravitation. F sub G is equal to big G M1 M2 over D squared. Yeah, EPE looks a lot like GPE. These ideas are analogous. So notice also that our formula for EPE looks a lot like our formula for Coulomb's law. The only difference is in Coulomb's law, D gets squared in the bottom. In the EPE formula, it doesn't. So you have to be careful when you're grabbing equations and trying to figure out what to do. Be very careful that you're grabbing the right one and squaring it when you need to and not squaring it when you need not to square it. So here's this slide. Our quantity is EPE, electric potential energy. It's energy, so it comes in joules, and it's a scalar. It's not wearing a hat, so that's good. We don't need to figure out components of this thing because it's a scalar, and scalars don't have components. So you could ignore this slide. The point, if we look at the formula here, notice you have a K in front of Q1, Q2 over D. In this version of the formula, instead of K, you have 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Ignore this. We're not going to use it this way. I'm just showing you this because perhaps in college physics you will see it written this way sometimes. It's just a different way of writing K in terms of a different constant. So when we were talking about GPE, notice in this formula there's a negative sign, which means that GPE was always negative unless it was 0 because the things were infinitely far away. But it was always going to be a negative number because masses are always positive, G is always positive, the distance was always positive. That is because gravity is always attractive, so GPE is always negative. It's always going to be a debt. It's always going to be energy you have to put in to the system to get away from the thing. When you're dealing with EPE, it's more complicated. So with GPE, masses are always positive, so GPE is always negative. With EPE, remember, you have positive or negative charges. So EPE will sometimes be a negative number, and sometimes it will be a positive number, depending on the kind of charges you have and whether they are attracting each other or repelling each other. So if you have like charges, so you have 2 positive charges or you have 2 negative charges, these charges repel. They don't want to be near each other, which means you had to put energy into the system to get these things to be close to each other. And now that they're close to each other, you can get energy out of it by letting them separate from each other. So look in bold at the bottom there, EPE will be positive with like charges. And if you have opposite charges, one is positive and one is negative, EPE is going to end up being a negative number. So this one would be a debt. These charges do want to be near each other, which means you have to put energy into the system to get them further separated. So EPE will be negative with opposite charges. So there it is, both rules together. And just like last chapter, you've got to come up with your own accounting system for figuring out how this works. So I'm suggesting 2 different ways of doing it. The first way is just let the signs of the charges do the work for you. So notice what would happen in this formula up here. If you have opposite charges, you're going to have a positive times a negative, so you'll have a negative EPE. So that would be like a debt. If you have like charges, so 2 positives, you're clearly going to get a positive. If you have 2 negatives, you are also going to get a positive. So if you have like charges, you would end up with positive EPE, which means these charges don't want to be near each other, and you can get energy out of this system by letting them separate. So that's one way of doing it. Just let the signs of the charges do the work for you. The other way is kind of more analogous to how we did it last chapter, which would be to just always think of the magnitude of EPE first. So just always think of it as a positive number first, and then afterwards decide whether or not it's really positive or negative. Do these charges want to be near each other because they have opposite signs, or do they want to be far apart because they have the same sign? Sounds complicated. It's a wordy explanation I've just given you. With practice, you do it a few times, and you figure out which way makes the most sense for you. So just like with GPE, if your charges are infinitely far apart, and so the D in the bottom becomes infinity, you have no EPE. EPE would be 0. And intuitively, conceptually, what that means is if your charges are very far apart, they don't have anything to do with each other. So you don't have to worry about the energy between them. So that's why if you're dividing by infinity, you end up with 0 EPE. So how would you do these problems? So let's say we have two charges, positive 2.5 microcoulombs and positive 3.5 microcoulombs. We're going to try to figure out the EPE of these things. So what is their EPE when they are very far apart? Well, you don't even need a calculator for this one. If they're very far apart, that's just shorthand for they're infinitely far apart. You're dividing by infinity, you're going to get 0. So when they're infinitely far apart, there's no EPE between them. Part B, what is their EPE when they are 0.650 meters away from each other? Okay, this time we have to, plug in the numbers, do the work in the calculator, and you end up with 0.121 joules. That's how much EPE they have when they're that far away from each other. So it's a positive number. What does that mean? These charges don't want to be together. You have two like charges, so if you've brought them together, there's potential energy stored up in that system. So you had to put energy into it to get them together. And if you let them go apart, energy will come out of the system. So, yeah. Well, it's not that it comes out of the system. It's that it stops being EPE. So look at this one, more complicated. We have three different charges, two of which, Q1 and Q2, are positive. The third of which, Q3, is negative. So how could we get the EPE of this arrangement of charges? So what you do is you determine the EPE of each combination, meaning each pair, but don't double count. So that means you would find EPE between 1 and 2, 2 and 3, and 3 and 1, and that's it. You wouldn't find EPE between 1 and 2 and 2 and 1, between 2 and 3 and 3 and 2. So don't double count, just do it once for each pair, and then you add up the EPEs. So you plug in all the numbers. If you're looking at those numbers, the top one, between 1 and 2, you're going to get a positive EPE because you have two positive charges. Between 1 and 3, you will get a negative EPE because one of the charges is negative, one is positive. And between 2 and 3, you will also get a negative EPE because positive and negative charges. So now you add them up, and you just add them like scalars. There's no direction. You don't have to do sub-zeros and find components. You just add them. So yeah, this will go a little quicker than some of the problems in last chapter. And when you add them, you get a negative total EPE. So what does a negative EPE mean? That means these charges want to be together. So a little explanation about that. Well, Q1 and Q2 don't want to be together because they're both positive charges. They're repelling each other. But if you bring Q3 into the mix, well, both Q1 and Q2, they both want to be with Q3. When you add up all of the EPEs, it ends up that overall you have a negative EPE. So this particular arrangement of charges, negative EPE, that means you're going to have to do work if you want to separate all of these charges from each other. So let's say that we had two electrons starting out at rest, a distance of 525 nanometers away from each other. So there's a metric prefix for you. The charge of one electron is that number. That's just the elementary charge. And the mass of an electron is 9.11 times 10 to the minus 31st kilograms. So how fast will these electrons be moving when they are very far apart from each other? So what piece of universal truth can we use to solve this problem? Well, it's one of the do now questions. This is a conservation of energy problem. This is a one with everything kind of idea. So step what are we trying to find? How fast will the electrons? We're looking for velocity. So velocity comes in meters per second. So step one is make a drawing, but actually it's a conservation problem. So you should make two drawings. You should make a drawing for your initial situation. You should make a drawing for your final situation. So look at the initial drawing and figure out what type or types of energy do we have in the initial one. Well, we've got two charges that are kind of near each other. So there's going to be EPE between them. Neither charge is moving, so there's no kinetic energy to worry about. We're not going to worry about Gpe or anything like that in this one. So the first one, we only have EPE. How about in the final sketch? Well, look, there are speed lines, so we've got masses that are moving, so we definitely have kinetic energy. And how far apart are these charges? Well, they're infinitely far apart. They are infinity meters away from each other. So we don't have to worry about EPE. So we only have KE in the final sketch. So step 2, write the law of conservation of energy. Turn the things into the things. So sigma E initial, well, initially there was only EPE. There was no external work being done here. And then on the final side, sigma E final. Well, at the end, we had kinetic energy in 2 different places. So I called it KE1 final and KE2 final. So now we're turning the things into the things. So replace everything by its formula. So we have all of that. The masses are clearly the same because they're both electrons, and electrons all have the same mass. The velocities would end up being the same. This is a very symmetrical situation. They're both starting at rest. They're both pushing on each other. They're going to end up moving the same speed. So I can drop all of these subscripts over here on the right. And that gets me here. So I have 1/2 mv squared plus 1/2 mv squared. Well, that's going to give me mv squared. Then you do the algebra. You solve for v. And at the end, you get this number, 21,961 meters per second, which I have chosen to write has 2.20, so I did some rounding with my sig figs, times 10 to the 4th meters per second. So yeah, conservation of energy. So the review questions. What is the formula for EPE between 2-point charges? EPE equals K Q1 Q2 over D. And of course, I will give you this equation, but it will be helpful if eventually you memorize it. Question 2, when is the EPE between 2 charges A? Positive. Well, it'll be positive when you have like charges. 2 pluses would repel, 2 minuses would repel. So you would have positive EPE. When is it negative? Well, it's negative when you have opposite charges. So opposite charges want to be together, so you're going to have negative EPE, meaning you have to put energy into them to get them apart. And when will EPE be 0? When they're infinitely far apart, because any finite number divided by infinity is going to give you 0. And that's it for part 1 of the slides. So hopefully you found that helpful.